Hello, good morning. Okay, so for today's tutorial, we only have two questions correct from the tutorial. So we'll also be spending some time going through a few past quiz questions. Okay, so you have an idea of the type of questions that have been asked. Okay, and we'll also go through the requirements document again. Okay, the project requirement document again, so you understand some of the key things to take note of. All right, so let's get started. Okay, then maybe the rest will join in along the way. Okay, so for tutorial 5, so we have two questions. So the first question is about certificate authority, all right, and why it is important. All right, so we saw that when you have a web browser, all right, when you try to connect to a website, it will automatically tell you whether it's a secure or not secure connection, all right, because it will check whether the certificate has been or the server has a certificate to authenticate whether this is a real or the actual website you're going to. All right, so why do web browsers, or how do web browsers enforce this requirement? Okay, so the way they do this is basically they store all their certificates in their certificate store. All right, and this is managed by the system admin. All right, and of course by the OS itself. All right, so if you okay, so when you are using any system, let's say you're using where is my pen not working? Give me a minute. Okay, so this certificate store, okay, is updated, all right, again either by system administrators or the web browser, okay, or by the OS itself. All right, so not anybody and everybody can just go in and update it. All right, but you have the ability to sort of revoke or delete some of the certificates if you think that you do not want to trust some websites, okay, or some servers that you're dealing with. All right, so if you open up the certificate manager in any browser, you can see the list of certificates that you already have in the browser, which means that all these are considered already approved, okay, for you to sort of access. Okay, but if you want, you can also manually delete some certificates. Okay, so if you delete a certificate, okay, doesn't mean you cannot go to the website. You can still go. Only thing is you will see that small message at the top left hand or right hand corner where it says that it is not a secure connection, or it is not encrypted or something like that. Okay, so you will see some message to warn you that it doesn't have a valid certificate. Okay, but you can still go ahead to access these websites. All right, so this is one example. So sometimes over here itself you might get some other warning message as well. All right, so when the browser, okay, wants to access any website, okay, the web server is supposed to present a certificate, and this is signed by a certificate authority. All right, so certificate authorities are sort of you can think of them as sort of the governing bodies that help to ensure that the websites are who they claim to be. Okay, just like in a simple sense, it's just like how you want to have a passport, correct? So when you want to travel, you want to go to another country, okay, you must the country must have some way of verifying that you are who you say you are, correct? And that they're not impersonating somebody else, correct? And how they do it is through the passport. And why do they trust the passport? Because it is issued by the government. So there is a trust that the government that issued this passport, okay, was able to verify that you are this person. So they are able to accept you into the country. Okay, so it is a similar thinking. All right, so the certificate authority is like a governing body, all right, that helps to give this certificate to a web server because they have verified who or what this web server is supposed to be doing. All right, it's not trying to do anything malicious, or it's not trying to do anything harmful to your system. So after they do their verification, they issue a certificate. All right, so when the browser, okay, wants to access it, it searches for its own certificate stock, all right, and uses it to verify the signature on the server's certificate. Okay, and from there, it sort of has a trust, okay, that this is a trusted or a reliable web server and a website that you're trying to access. Okay, but in the case where it doesn't have a certificate, okay, to verify its identity, you will get some form of message. All right, of course, it doesn't mean you can't access. Like I said, if you click on this advanced, or some other browser, you click on some other uh, advanced or more options button, you will still be able to go ahead, correct? But they will just give you some warning that it is not safe. Are you sure you want to proceed, and things like that. Okay, so that is the whole idea of the certificate authority, correct, and how it helps to manage the safety of the internet. Okay, so in this question two, again, this is just to give this importance that the private key that you generate, okay, though in our case we generate for our robot Alex, okay, you must always remain on Alex. Okay, why? Because the private key is the one that is able to authenticate that this message is coming from Alex. Okay, so if once a private key goes out, what happens? That means somebody else can choose to pretend to be Alex and send and receive messages. Okay, and then that's where all the haywire happens. Correct. So this is a case study, all right, where something like this happened in the past, where a CA reseller, okay, Trustico, somehow managed to get 23,000 private keys. Okay, so it's not very clear how they got these private keys, okay, but somehow they managed to get hold of these private keys. Okay, so this Trustico is a reseller, correct? The main person issuing the web certificate is DigiCert, okay, and they asked DigiCert to cancel all the websites that are related to these private keys. All right, and DigiCert refused to do it, so the CEO had to force them by emailing them the private keys. Okay, so by making it known that I'm sending this out to you, that means I know this information, then they have no choice, correct? They have to revoke all the certificates. Okay, and once they revoke the certificates, okay, they are all those websites will no longer be directly accessible. Correct, you will get that warning message coming out. Okay, so why do we want to revoke the certificate when the private keys are compromised? Okay, again, it comes back to the security, because now anybody can set up a fake website, okay, and pretend to be a legitimate website. Okay, because once I know your keys, all your encrypted messages, I can just decrypt, okay, using the private key. All right, so as far as you're concerned, all right, your browser will still not be able to detect anything, because the certificate that you have of the website is still considered signed. All right, it is considered signed, so it is still a trusted website. Only thing is the actual website is no longer functioning, but somebody else has set up a fake website and using the private key to communicate with you. Okay, so that is why it is important. Okay, the moment private keys are compromised, you need to revoke the certificate and go through the process again. Okay, so this is again, I think, just to give you the idea of this whole idea of encryption and why all this is important. Okay, I know this last topic on the TLS and networking is quite a lot of material, correct? So you're not expected to go into all the details, okay? Though we have given you all the libraries, correct? So as long as you understand the process, okay, I think that is good enough. Okay, but later we will just go through some sample questions and the requirements. Okay, so you can see whether you want to go ahead with using this, or you want to stick with what you already have working for you in terms of the SSH and VNC and things like that. Okay, so Yeah, so basically we only have those two short questions. All right, so nothing much in terms of material because the rest of it we already covered in the last tutorial. Okay, so let's go through some past quiz questions. Okay, to get some idea of how to approach them. Okay, you all already have these questions with you? Were they uploaded before? Yes, no? Okay, yes. Okay, good. So you already, hopefully you've seen these questions, okay? But anyway, let's just go through one by one and analyze it. So the first question, we have a communication system with a baud rate of 9,600 communicated as a sine wave. Okay, that can be transmitted at 4 voltage amplitudes and 2 phase shifts. Okay, what is the maximum bit rate achievable on this system? Okay, so if you remember last time we talked about baud rate, we had a discussion. So we know that baud rate is equivalent to symbol rate. Okay, it's not actually bit rate, right? It depends on what it represents. Okay, so now we know that the actual data has two different types of variation to it. Okay, so one is phase. So you can either go with 0 degrees phase or 180 degrees phase shift. So there is two possibilities in terms of the phase. In terms of voltage levels, there are 4 voltage levels. Okay, here they only draw two. Right, this is one voltage level. This is another voltage level. Okay, so here they only draw two different levels, but it is already said there are 4 different voltage levels. Okay, so in terms of the total number of combinations is basically 2 times 4, which is 8. Okay, so I have a total of 8 different possible combinations in the way I transmit any particular symbol. Correct. Okay, why? Because when I transmit it at 0 degrees phase shift, I have 4 different voltage levels. When I transmit at 180 degrees phase shift, I also have 4 different voltage levels. Okay, so it's total of 8 possible symbols that I can transmit. Okay, so that is the first thing you must look at. How many different symbols am I able to support with this current sort of design that I have? Okay, so I know that I have 8 symbols. Okay, so the next thing is how many bits to represent 8 symbols? So we have 3 bits. All right, so we have 3 bits, or we need 3 bits to represent 8 symbols. All right, we need 3 bits to represent 8 symbols. Okay, okay, so you can think of 8 symbols as 8 different possible combinations, right, in how I can transmit my data. Okay, so that means that whenever I transmit one particular symbol, it is equivalent to transmitting 3 bits of information. Okay, whenever I transmit one symbol, it is equivalent to 3 bits of information. Okay, to put it simply, okay, maybe I draw it out here. Imagine that right now I split it into 0 degrees and 180 degrees. Okay, so under 0 degrees, I may transmit a signal like this, which is 1.25 volt. I can also transmit a signal that is slightly bigger. Okay, that is 2.5 volt or something like that. Okay, then it's something even bigger. Okay, then there will be 3.75, and finally it will be 5 volt. Okay, so I can transmit 4 different waveform, okay, at different amplitudes. Okay, and at the same time I can transmit the same 4 different waveform with 180 degrees phase shift. Okay, with different voltages. Okay, that means I have a total of 8 possible combinations here. Okay, 8 symbols, 8 different combinations. So every time I transmit one particular symbol, it is equivalent to 3 bits of information. All right, so since I'm transmitting at a baud rate of 9,600, so 9,000 600 multiplied by 3 will give me E. Okay, the answer here. Okay, so that's how you get the answer here as 28,800. Does anybody have any questions about this? Okay, so why is it 3 bits? Because you have a total of 8 symbols. So 8 symbols means 8 possible different ways in which you can represent data. So if I want to represent data with 8 different possible ways, then I need 3 bits because 2 to the power of 3 is 8. Okay, so you must always come back to in terms of how many bits I need to represent all the different signals that I have. Okay, so if you come back to the very basic, okay, okay, and I say that I have only ones and zeros, correct? Ones and zeros. Then what do I have? I only have 2 possible values, correct? So at any point of time, I can only transmit 1 or 0. All right, that means when I transmit a bit, it can only represent 1, I can only represent 0. Okay, but now if let's say I break it up, okay, into 0 and 5 volt, correct? 0 and 5 volt means it's only 1 and 0. Okay, so if I have 5 volts means it is considered logic 1, 0 means 0 volt. So every time I transmit a single bit, okay, a symbol, so this is considered one symbol. When I transmit one symbol, it is equivalent to 1 bit being transmitted. Okay, but if I now just let's say look at voltage alone, okay, instead of 0 volt and 5 volt, I say I have 0 volt, okay, 1.25, 2.5 and 3.75, for example. Okay, so I transmit using 4 different voltage levels. So this is 1 bit, this is one symbol, this is another symbol. Okay, so this is another symbol and this is another symbol. Okay, so when I transmit one symbol, okay, at each point of time, how many bits am I representing? Because right now I have 4 different voltage levels, so 4 different symbols. So 2 to the power of 2 will be 4. So I can say that this 0 0, when I transmit 0 0 means it's equivalent to 2 bits. You know, so the symbol must be mapped back, okay, to the number of bits. Okay, so if you have number of symbols that are not let's say you have like a question here, you have 10 symbols. Okay, if you have 10 symbols, then how do you calculate? Because if you have 10 symbols, okay, then you need minimum 4 bits. Okay, so you need to have 4 bits to represent 10 symbols. Okay, so you need enough bits to represent all the symbols, okay, in your system. Okay, unless of course you support 10 symbols but you only use 8, for example. Okay, so you can always say that, okay, I have 10 symbols. Okay, how? Okay, so maybe over here I have 2 additional voltage levels. I can say 0 volt, 1.25, 2.5, 3.75, 4.25, and 5. Okay, sorry, 5. So 5 times 2. So 5 times 2, let's say I got 10 symbols, correct? So I include 0 inside. Okay, so now I have 5 times 2, which is 10 symbols. All right, but I can say that even though my system supports 10 symbols, I will not transmit anything at 0 volt. Okay, so I only transmit at only 4 different voltage levels, which is 1.25 to 5. There I don't need to factor in the 0. Okay, so it depends on how many symbols you are going to use in the transmission. Okay, so if you say I need to use all the symbols for transmission, then you need to have minimum 4 bits. Correct? Because 3 bits will not be enough to support 10 different symbols. So you need minimum 4 bits. Okay, so of course, if you have 4 bits, then you have additional bits that will not be used. Correct. So in that case, that means maybe if you use the lower bits, then you go from 0 all the way to 9. Correct. Then the rest you do not use for now. Okay, because you only have 10 symbols. Yeah, so you basically need to make sure that the number of bits you select must be enough to support all the symbols you need to support. Correct. So if I have 10 symbols, 3 bits is not enough, 4 bits is more than enough, but that is the smallest number that supports. So you have to go with 4 bits then. Okay, so if you use more bits than needed, okay, then you are wasting I would say you're wasting your sort of bandwidth, correct? Wasting a bandwidth. Okay, so for example here, instead of 3 bits, you transmit 4 bits. Okay, so instead of 3 bits for each symbol, you use 4 bits. It can still work, but then you are transmitting a 4th bit, but it's not going to carry any information. Okay, it's not going to carry any additional information. Okay, so your system will still work. Okay, because you transmit 4 bits, you receive as 4 bits, but you are transmitting an additional bit that does not carry any valuable information. So it's a waste of your bandwidth. Okay, so generally you should always look at what is the minimum number of bits required to make sure that you can represent all the symbols in your system. Okay. Okay, so let's go on to the second question. Okay, so in this question is about testing the Indianness of a 32-bit system. Okay, so let's first understand this a bit better. What is this Indianness? All right, so let's take 32-bit data. Okay, so this is the most significant bit, and this is the least significant bit. So let's assume my data is 0x11, 22, 33, and 44. Okay, this is my data. And how will this data be arranged in different systems? Okay, so let's first have the address. So let's assume that I'm going to store this in address location A000, A001, A002, and A003. Okay, so this will be the 4 different address locations, okay, for the 4 bytes. Okay, so if I want to use a little Indian system, Okay, the least significant byte will always go to the lowest address. So um, so the 0x44 will come here, 0x33 will come here, 0x22, and 0x11. Okay, the least significant byte goes to the lowest address. Okay, and in the big Indian is the other way. The least significant byte goes to the highest address. So that is the order in which data will be arranged depending on what type of system it is. Okay, so this is your big Indian. Right, so that is the first thing. Okay, we must understand how data is arranged in a little Indian format or big Indian format. Okay, so let's look at the first example here. Okay, so let's look at solution. Okay, let's look at the data. Okay, so the data here is this test, which is 0, 1, 0, 0, 0, 0, 0, 0. Okay, either this or this. These are two possible combinations. All right, and then we are trying to do a check. Okay, to see the lowest address. Is it the leftmost byte or the rightmost byte? So first, let's look at this 0, 1, 0, 0, 0, 0, 0, 0. So with this data, okay, so I have this data 0, 1, 0, 0, 0, 0, 0, 0. Okay, so if this was a little Indian system, then the 0, 0 will come here. Okay, 0, 0 will come here. This is the last least significant byte, and then go up. Okay, if this was a big Indian system, the 0, 1 will come here, and it will be arranged this way. Okay, so that is how this would have been arranged. Okay, depending on whether it was a little Indian or big Indian. Okay, now, so that is the arrangement of that first data, that 0x01 00 00 00. Now let's look at this. Okay, so what are we doing here? So let me go over to another. Okay, so let me just show you what will happen when you run. This. Okay, so here I have the same data 1 1 2 2 3 3 4 4. Okay, and I have the same code. Okay, the same code that you see over here. Okay, so what are we doing here? So this M% test is what? The address of this variable, correct? So you have all done CS 1010, so you understand the concept of pointers, correct? So in the concept of pointers, when you say M% test, you are taking the address of this variable, correct, where it is stored in memory. Okay. Now, when I take the address of this variable, okay, it tells me the address, but I want to reference it as a character. Okay, why? Because this is actually 4 bytes. It is 4 characters, correct? Because it's a 4-byte integer. But I only want to access it as a character, so I cast it as a character over here. Okay, and then I put the other pointer notation here because I want to access the variable or the actual data that is pointed to by this address. Okay, but I'm only interested in the character portion of it. That means the first byte of it. Okay, the very first byte of it. Okay, so if I run this, okay, so you can see that the value here is 44. Okay, so this value here is 44 means it is pointing to the least significant byte. Okay, so that tells me that this is a little Indian system. Okay, why? Because the address is always starting from the lowest address, correct? And the lowest address is the least significant byte. Okay, which means this is a little Indian system. Okay, now let me just show you the step by step what is happening. So you can see what happens if I do it progressively. Okay, so this code is the same, only thing I have broken it up step by step. Okay, so what I've done here is I have created specifically a character pointer. Okay, so instead of lumping everything together over here, what I've done is I created a character pointer, and the variable test, again, I'm taking the address, but I'm only interested in the character portion of it. Okay, and then I assign the address over here. So here I can print out the address. Okay, but what I'm interested in is the actual value, which is here. Okay, so when I print out this line asterisk test address, is going to point to this test variable, correct, at the starting address, and print out the character of it, the character value that is at the address. Okay, so let me run this and I'll show you what you get. So this is the address. Okay, so we don't need to worry about the address. Okay, but you can see that I get the same value. That means what I'm doing is I'm pointing to the starting address of this variable and printing out the first character, which is 44. Okay, so technically it is equivalent to just pointing to this last byte over here, which is the lowest address. Okay, now what I'm going to do is I'm actually going to increment my address. Okay, so test address is originally pointing to where? Is pointing to the test, all right, which is this variable. So it automatically points to the smallest address. So when I increment by 1, okay, since my test address is a character pointer, so when I increment by 1, you increment to the next byte. Okay, increment to the next byte. So when I increment my address and then I access the next variable, what will I get? I'll get the one that is after 44, which is 33. Okay, and then I can do that again and again. Okay, so if I run the whole thing here, you can see that I print out the whole sequence here. Okay, 44, 33, 22, 11. Okay, why am I able to print out the whole sequence? Because each time I increment my address by 1 and then access the next character, and so on. Okay, so what I want to show you is what we are doing here. Okay, is basically we are trying to access the variable, all right, through a pointer, but we're only interested in the character portion of it. Okay, the character portion of it. So coming back here, when we are accessing this, all right, if it is equals to 1, what does that mean? Okay, if it is equals to 1, that means, okay, so the first thing you understand is when I do this statement over here, I am pointing to the starting address of the variable test. Right, I'm pointing to the starting address of the variable test. So if I'm pointing to the starting address, so let's assume this is the starting address, and if it is 1, it is actually a big Indian system. Does it make sense to you? If I'm pointing to the starting address and I get a value of 1, that means the most significant byte of this integer is in the smallest address. Okay, the most significant byte is in the smallest address, so it is a big Indian system. Okay, so this is wrong, correct? This is not true. It's not an Indian, it's a big Indian. Correct. So actually, this is the correct answer here. Okay, because it's the same data, correct? And I'm testing whether the byte at the lowest address is 1. So this is the correct answer. So this is the wrong answer. So similarly, you can check here. If the value I'm pointing to is 0, if it is 0 means it is this. That means the least significant byte is the lowest address, and that it should be a little Indian system. It's not a big Indian. So this is wrong also. Okay, if it is 1, if the variable is 1, that means it is what? So change the color here. Okay, so if the data is 1, that means it is 0, 0, 0, 0, 0, 0, 0, 1. Okay, so if the data is 1, then for little Indian system, it should be here. 0, 1, okay, 0, 0, 0, 0, and 0, 0. And for big Indian system, it should be over here. Okay, so if the data is a 1, okay, and if I check the lowest address, and if the lowest address is a 1, the lowest address is a 1 means, which is this, it should be a little Indian system. Correct? But here it says big Indian, so this is also wrong. Okay. Okay, so I think this one, both solution 3 and solution 5 is the same. This is also wrong. Okay. So the correct answer is this, D. Okay, so the important thing you must understand is the order of the arrangement. Okay, so always remember that for a little Indian system, the least significant byte will be the lowest address, and then you go up. Okay, just so you just remember one of it is enough. Then the other one is just the opposite. Okay, and whenever you are using a character to point to an integer variable, you always start off with the lowest address. Okay, does anybody have any questions for this? Okay. Okay, so for solution 5, yeah, this is a character. Okay, so a character is only a single byte. Okay, so in this case, your solution 5 cannot check whether it is a big Indian or little Indian, because when I check for this will be true. Okay, so this test is true, right? Because test is 1, and when I point to the address of test and cast it to character, I will get a 1. All right, but I cannot deduce that it is a big Indian because of this test, because the variable is only a character. Because a character only occupies a single byte. Okay, you can only test the Indianness in a multi-byte data. Okay, so let's go on to the next. Okay. Okay, so in this question, basically you are implementing what we call a soft. This is what you call a soft serial. Okay, so where if for example you are not able to use the UART, okay, for some reason, okay, and then you want to manually create a serial protocol. Okay, so this is one way of doing it. Okay, where you manually toggle the lines, okay, at a sort of periodic intervals. All right, and what is shown here is you have two Arduinos. All right, they are trying to talk to each other, okay, using this. And so on one side for the transmit, okay, we are using timer 1, okay, and the other side to receive we are using timer 2. Okay, similarly we are also given the code for the transmit and receive, okay, the send byte and receive byte. Okay, so first let's try to understand what is happening here. Okay. When I look at the byte, so let's look at the send byte. Okay, so whenever I want to send a byte, I need to call the send byte. All right, and what will the send byte do? Okay, so the send byte will pull the line low. So originally the line is high, and the send byte will first pull the pin low. So this is pin 4. So TX is pin 4. I pull it low. Okay, and I pull it low for 500 microseconds, which is 0.5 millisecond. Okay, and after that, what do? I say that I set up the code to have timer 1 trigger every millisecond. Okay, so timer 1 will be triggering every millisecond. So what happens is the very first interrupt, that means after 1 millisecond, the interrupt happens, and then I start to transmit data. Okay, so how I transmit data, okay, is through analyzing the byte to send and deciding whether the pin should be high or low. All right, so let's look at the timing first. So we know that I first have to wait for half a millisecond, and after 1 millisecond, another 1 millisecond later, another 1 millisecond later, I will send the start sending the first byte. Okay, I'll start sending the first byte. So the first byte, and then the second byte, and so on. Okay, so this is the first byte, or sorry, first bit that I sent. Okay, and then second bit, and so on. Okay, so first half a millisecond I wait, and then 1 more millisecond for the first interrupt to trigger, and subsequently is every bit. Okay, for the receive byte, okay, so this is what I'm transmitting over. How about the receiver? So over at the receiver, I'm receiving on pin 3. So I receive on pin 3. Okay, and I wait while digital read 3. That means what? That means while 1. So this is considered a while 1, right? That means while I'm still 1, that means I'm idling. That means I'm not transmitting new data. I stuck in this loop. The moment the transmit line pulls it low, then I will come out of this loop and come here. But I'll come out of that while 1 loop and I'll come here. And inside that loop, I will wait for 1.5 milliseconds. Okay, so this is the trigger point, right? The moment the line 3 detects that it has gone low, I will come out of that while loop, okay, and then I will wait for 1.5 milliseconds. Okay, and after 1.5 millisecond, I also set up timer 2 here in this case to trigger every millisecond. So every 1 millisecond later, I will wait. So the first interrupt will come in 1 millisecond later here. So this is the first interrupt. Okay, so this first interrupt that happens on the receiver side will coincide with the end of the transmission of the first bit. for the transmit side. Okay, will coincide with the end of the first bit for the transmit side. All right, so that makes the first option here true. Right, the bits sent are read by the receiver at the end of each bit period. Okay, at the end of each bit period, I will start to read the incoming bits. The bit rate of this solution is 1000 bits per second, all right, which is true. Why? Because both of them are set to trigger every millisecond. Okay, so this is just to indicate that this is the duration of one bit and this is another bit. Okay, there's nothing here. Okay, I'm just trying to demarcate between the different bits. Okay, so the transmit and receive both interrupts are triggering every millisecond, which means it is 1000 bits per second. So it is also true. Okay, so the first statement is true, second statement is true. Now the third statement, bits sent are received in reverse order. So let's look at how they are sent and how they are received. So if you look at this, the data that I want to send is byte is copied to this variable called byte to send. And in this byte to send is a global variable, correct? So what do I do here? This byte to send, I end with 0x1. So when I end with 0x1 means, if this is the byte, 0x1 means I only take the last bit. Okay, I only take the last bit. All right, and then if it is a 1, I say high. If not, I say low. And then I do a shift. Okay, so what do I do after I transmit out? That means assuming my data is, let's say 1001 0011, I first transmit out the 1, correct? And after that, I do a shift. So everything gets shifted. So it becomes 01001001, correct? Then the next bit, the next bit, the next bit. So I keep shifting out the bits. Okay, starting from the least significant bit. Okay, so the order is from the right to the left. So taking this byte to send, I start from here and then I go in this direction. Okay, from the least significant bit all the way to the most significant bit. That is the order in which I transmit out the data. Okay, how about receiving side? In the receiving side, what do? I read, okay, the line tree, okay, and then I see whether it's 0 or 1. If it's 0 or 1, I update a bit called bit to write. And what is bit to write? Bit to write starts with 1. So the bit to write is always starting with the least significant bit. Okay, and after I update one bit, I go to the next bit. Why? Because I shift to the left by 1. Okay, so every time I update the least significant bit, then I go to the next bit, to the next bit, to the next bit. So I also start from the least significant bit and I update to the most significant bit. Okay, so the order in which I transmit and the order in which I receive is the same. Okay, the order of transmission and the order of receiving is the same. Okay, so this is not true. Okay, it's not reverse order, it's the same order. Okay, the order in which I send and the order in which I receive is the same. Okay, pin 3 is used for TX and pin 4 for RX. No, okay, we just saw that pin 4 is for TX and pin 3 is for receive. So this is also not true. And ground between two Arduinos must be connected. Okay, this we already have done in the lab. Right? Whenever you have different systems, you must always connect them to a common ground. Okay, to make sure the reference point is the same. Okay, so that sort of okay. So for option 2, why is 1000 bits per second? Is because both of them are set to trigger the interrupt at every millisecond. Okay, so that means in 1 second you have 1000 interrupts, which is 1000 bits per second. Okay, so the bit to write is starting from 1, correct? Which means it is the least significant bit over here. Okay, so the very first bit that I receive, I will update the least significant bit. Okay, and then I will shift the bit to right to the left by 1. That means after I update the least significant bit, I will move this bit to right to the next bit position, and then the next bit position, and so on. Okay, so since I have 8 bits, okay, so I will start off with the least significant bit, and then I'll keep shifting to the left one by one. Okay, to update each bit as it comes in. Yeah, the bit to write and byte to send is basically, because in the byte to send, we are manually shifting the entire byte, okay, until you finish all the 8 bits. In the case of bit to write, we are just updating which particular bit we are updating. All right, so since I start from the least significant bit, okay, then I move to the left one by one. Whereas the byte to send is the entire byte, all right, that I start with, okay, but I push out bit by bit, starting from the least significant bit. Okay, wait, got a lot of questions. Okay, so let me show this up. Maybe I demonstrate this pattern, then you see what's happening. Okay, so I think you're confused between the byte to send and bit to write. Okay, so if let's say this is my byte to send, this is the byte to send. We know that I do an AND with 0x1. That means I first extract out this last bit, correct? I transmit this over. The very first time, the bit to write is 1, correct? So when I receive this 1, okay, then what I will do is, since I receive it as 1, the byte received. So the byte received is updated based on the bit to write position. So what is the bit to write position? Bit to write position is 1. Okay, let's look at the very first bit. Okay, the very first bit. So when I receive the very first bit, okay, since the very first bit here is a 1, when I receive, I will update the bit to write as 1. So the bit to write is originally 1, correct? So this value here will become a 1. Okay, and then what will happen? I will shift the bit to write to the left by 1. Correct? I will do this operation, which means that for the next interrupt, I'm supposed to update this bit. Okay, so the bit to write is just a single bit that is traversing from right to left. It is not the actual data. Okay, the actual final data is inside this byte receive. That is where the actual data is stored. The bit to write is telling me the position that I should update. Okay, so after I start off with the least significant bit, okay, then I shift to the left by 1. Okay, so now we know that this would have shifted to the right by 1, so I have this new data over here, correct? Okay, so everything shift to the right by 1 and so on. Okay, so now this last bit is going out. Okay, this last bit here is going out. So again, another one is going out, correct? So another one goes out. Again, I will receive the data and I will update the bit to right, which is this. Okay, so again, I will check whether the bit received is 0 or 1. So if it is 0 means that particular bit will be cleared. If it is 1 means I will OR with the bit to right. So it will become a 1. Then again, I shift. Okay, so again, I shift. Correct. So the 0, 0, 1, 0, 0, 1, 0, 0. Correct. Now I shift out a 0. So when the 0 comes in, okay, so before that, I would have already shifted my bit to right to this position. All right, so it's no longer here, it's in the next bit. All right, so since the 0 comes in, I will make sure that that bit to right is clear because I end with a complement of bit to right, so it will be a 0. All right, so that is what is happening. The bit to right is keeping track of which bit I'm updating, okay, for every bit that I receive. Okay, this bits received is just to keep track of the count. Okay, that I have received 8 bits of data. Okay, the actual data that I receive is inside this byte receive variable. Is it clearer now? Okay, the bit to right is shifting to the left by 1, correct? Because every time I keep updating the bit position to the left. So I start with the least significant bit and then I keep updating that the position is now 1 bit to the left, 1 bit to the left, and so on. Okay, so let's move on first. Okay, if you still have questions later, okay, at the end we can come back. Okay, so let's go on to this question 4. So in this question, similar to what we did in the studio, but we have a structure, okay, which we have declared, and we have the sender and the receiver. So both using the same data structure, the T data, okay, and you send this, okay, and over the receive side you receive it. So what is the question? So the receiver gets the following. So what did the sender send? The sender sent this information, okay, but receiver received this. Okay, so let's look at this. So the sender side, okay, what we sent was C is 15, Y is 0x1F2D, and Z is 0x22FC. Okay, so in terms of the serialized data, okay, it could look like this. So 15, then 0x1F, 0x2D, 0x22, and 0x. Let me erase this. Looks a bit. Let me draw it again. 22 and FC. Okay, so the sender send this, all right, but the receiver receive this. Okay, so which of the following statements is true? Okay, so if you look at this, okay, what you can see is for the receiver, it received the character correctly. Okay, but the first integer, instead of taking 1F2D, it became 2D22. That means it started over here. That means the Y started here. Okay, and then the Z, if you look at it, it started at FC 2F. That means it started at FC and then 2F. So 2F is nowhere here. All right, 2F is not part of the sender data. Okay, so from this, how do we interpret this? So we need to relate back to our understandings from the studio. So we know that when we have our compilers compile data, sometimes they will do padding, correct? Okay, because of the way they or the rules they follow in terms of the arrangement of data. Okay, so in that sense, okay, we can say that for the Y variable, instead of starting at 1F, it started at 2D. Okay, that means it interpreted the character C, okay, and that it should have a padding to make it 16 bits long. That means that every structure element is supposed to be 16 bits long. Okay, so even though it reads as 16 bits, but since the variable is declared as a character, so this is a character variable, you still are able to interpret it correctly. Okay, similar to our studio. If you remember our studio also with the padding issue, the character will always interpreted correctly. Why? Because the data type is still character. Okay, so the padding only looks into how much bytes I access from the actual serialized data, but I still interpret only the last byte because I declare it as a character variable. Okay, so it sort of links back to our studio. All right, so even though I may interpret it that there is padding, okay, but the actual padded values don't affect me because I still interpret the data type as a character, so I only look at the last byte. That is why the character is still interpreted correctly. Okay, the Y variable, okay, it starts again 16 bits later, so it's 2D and 22, and this Z is FC plus whatever is here, okay, plus whatever is here. So in this case, it could be just the variable 2F. Okay, this 1F is the data that is transmitted, correct? The data that is transmitted from the transmit side over here. Okay, so with that, we can sort of say that the receiver actually pads structure elements to 16 bits. Okay, the sender compiler does not. and they have the same Indian step. So there is no change in the order of the data. Okay, there's no change in the order of the data. So it is just a matter of the structure padding. Okay, the elements padding. So in the receiver side, okay, when I created this variable, it expected that every element will be 16 bits long. Okay, but whereas on transmitter side, this is 8 bits. This is 16 and this is 16. Okay, so that padding on the receiver side makes it interpret the structure differently. Okay, so that is why the answer here is B. Okay, so this last value could have been anything. Okay, so this 2F is just a random value. It could have been anything. Okay, it's just that it took in whatever that was in that additional memory space. Okay, so any questions on this? Okay, so this is the same as your studio, correct? That means if you remember your studio, you have the same issue, right? When you declare a character from your Arduino side and your character on your RPi side, okay, there is a padding that is automatically generated by the RPi compiler, which is not done on your Arduino compiler. All right, so that is why we had to do the padding. So remember, we had dummy characters. Okay, so after the char, we had dummy characters. Okay, to compensate for the padding. So the same thing is what is happening here. Okay, so on the you can think of it as the transmitter as something like the Uno, okay, and the receiver is something like the RPi. So the or some other board. Okay, so it's not RPi, but it's some other board where the Uno interprets character as character. Okay, it does not do any padding in the structure, whereas this board that is now receiving this data, okay, the compiler expects padding for the structure elements to be all 16 bits. Okay, so since it wants everything to be 16 bits, it looks at everything as 2 bytes. So the first element is 2 bytes, second element is 2 bytes, third element is 2 bytes, and so on. Okay, so even though I transmit as 1 1 5 1 F 2D 22 FC, but it interprets as 1 5 1 F as the first element, 2D 222 as the second element, FC plus whatever is beside it as the third element. Okay, so that is the reason why it is interpreting it this way. Okay. Okay, so the Indianness has not changed because the order of bytes is still the same, correct? So if you look at it, we still have the order is the same because you can see that for example the 1F2D is still the same as 1F2D which we sent. 22FC is still there. Even though we are now interpreting it at different boundaries, the order of the way the data has been arranged is still the same. Okay, so there is no difference in the Indianness of the data. Okay, so the order is the same. It's just that we are now interpreting it at different boundary because of the padding. Okay, so for this question, we send this bit pattern at 9,600 bits per second. Okay, and so the receiver side is going to sample it at double that bit rate. Okay, so we are asked to assume that the receiver samples in the middle of a bit with respect to its own bit rate. Okay, so let's see how to do it. So since I'm now going to sample at double the bit rate, okay, what I need to do is I first draw out this data, correct? So this is one, so this is one, this is one, and then zero, okay, and then one, and then one. Okay, so basically what we need to do is we just need to sample it. So rightfully, if I'm transmitting at 9,600, okay, we say that the this is the interpretation 11011. Okay, now the receiver is going to sample it, okay, but it's going to sample it at double the bit rate. Okay, and we say that the receiver samples in the middle of a bit with respect to its own bit rate. So if it is double the bit rate, means it is basically going to take 2 samples per bit. Okay, so instead of this representing 1 bit, okay, this is going to represent 2 bits, and this is going to represent another 2 bits, and this is going to represent another 2 bits, and so on. All right, because I'm now going to sample 2 times per bit. Okay, 2 times per bit. So this will be interpreted as 1 1 1 1 0 0 1 1 1 1. Okay, so you're just splitting up each bit into 2 separate bits, okay, 2 separate samples. Okay, so here they just give you some idea of how you can draw it out. Okay, but I think if you just sketch it out, also you should be able to see or interpret it correctly. Yeah, it is half the bit rate. Okay, so it is 2 symbols will represent 1, correct? So it will be 1 1 1 1 1, correct? Okay, if it is half the bit rate, okay, so if we just take this interpretation, okay, so let's say now instead of 19,200, it is 4,800. That means it's half, correct? So what happened? So if I were to draw the same data, okay, 1 1 0 1 1. Okay, so I need to represent it as let me just see. So every 2 bits is considered 1 every 2 bits is considered 1, and this is considered another 1, right? So these are the 3 boundaries. So 1 1 will be 1. This is a 0 to 1 transition. So 0 to 1 transition is a sampling it in the middle, correct? So this is a 1, and this is a high to low transition. This is a 1 1, and this is a high to low transition. Okay, sample in the middle means it's also a 1. Okay, because based on the example given here. Okay, if I happen to sample in the middle of a transition, okay, if it's high to low, so I take it as 1. If it's low to high, I also take it as 1. Yeah, so again, it depends on how this sort of interpretation lines are given, correct? So based on this information, we can say it will be 1 1 1 if, let's say, I were to sample it at half the bit rate. Okay, so any questions on this? Okay, so let's go on to the last question. Okay, so this one is on the ransack algorithm. Okay, so for this, basically what we have is we are given the sort of algorithm here, right, from the tutorial. And what we are asked to look at is this. Okay, so we are told that the data point, each data point has 16 bytes in total, and the LiDAR is scanning, okay, uniformly. Okay, and the bandwidth used to communicate data points is 46.08 kbps. So the LiDAR unit is placed at the center of a perfectly square and empty room facing random direction. So what is the smallest consensus value below that will cause the ransack to fail to detect any of the 4 walls? Okay, so what is this consensus first? So the consensus is basically the point of agreement, correct? That means if I have enough points, okay, that is above this consensus, that means I need, it's just like a minimum number of votes. All right, if I say I have this number of votes, then I agree to do something. Okay, so you can think of consensus as a minimum to come to an agreement. So if I have the number of LiDAR data readings that are above this consensus, that means the minimum that I need, then I can agree that there is a actual obstacle or object there. Okay, if not, then I will just take it as some random points. Okay, there is no defined obstacle at this point. Okay, so I need to have a minimum number to hit to say that, okay, this is really, there is a line there, there is an edge, or there's a wall there or something. So I need a minimum number of points. That consensus is the minimum number you need to come to an agreement. Okay, so what they're asking us is, what is the smallest consensus to which you will fail? Okay, to detect any of the 4 faults. So
everyone. No.
so the first thing is, so we have a wall. All right, we're going to place the wall, place the LiDAR somewhere. Okay, so it could be pointing any direction, correct? So it could be pointing here, it could be pointing here, it doesn't matter. Okay, so let's assume that it is facing in this direction. All right, that means I'm going to do a So to detect any of the four walls. So let's look at the information first. All right. So the communication speed is 46.08 kbps. All right. So I have a total of 46,080 bits per second. Sorry, bytes per second. Okay. And each point has 16 bytes. Okay, each point has 16 bytes. So if I divide this by 16, I will get 2,880 points. Okay, so in 1 second, I get 2,880 points. All right. Now, for this 2,880 points is divided across the entire full cycle, correct? Because every time it spins, it generates all these points for us. Okay, so if I take 2,880 divided by 360, then I need 8. So I get 8 samples per degree. Okay, that means every time I turn by 1 degree, I get 8 samples. Okay, every time I turn by 1 degree, I get 8 samples. So in order for me to detect any wall, okay, okay, minimum I need is to scan 90 degrees. Correct. So if let's say I face any direction, I need to be able to scan from here to here. Okay, so I need to be able to scan at least 90 degrees to capture that wall. Okay, I need to be able to scan 90 degrees to capture a wall. That means 90 degrees times 8 will give me 720 samples. So I need 720 samples. Okay, so if my LiDAR is moving in this direction, when it bounces off this wall, okay, for this 90 degrees, I will get back 720 samples, okay, of points. Okay, 720 samples of points. So if I get back 720 samples of points, if my consensus is 530, okay, my consensus is 530, and I get 720 means I can confirm that yes, I am above my consensus, so I can detect that this is a wall. If it is 630, again, I can say that I'm above my consensus, so I can confirm it's a wall. Okay, but the moment my consensus is set at 730, then 720 is going to be lesser than 730. Okay, which means that any wall that I face, I will always get lesser number of points than the consensus, which means I will fail to detect any of the four walls. Okay, because the consensus is the minimum number of points I need to come to an agreement, correct? That this is a valid wall or obstacle or something. Okay, so as long as I am above the consensus, then I can agree. But if I'm always below the consensus, then I can never make a decision to say that there is really something there. Okay, so if my consensus is set at 730, okay, then I will always fail. So this is the point where the smallest value by which you will start to fail and not detect any of the four walls. Okay, which is what is sort of given here. Okay, so this is just to again just to sort of think back of how the LiDAR operates. Okay, so we use 90 degrees because for a square, okay, for any square, to detect there is a wall, I need to scan from one edge of the wall to the other edge of the wall. Okay, and that will always be 90 degrees. So that's why I need to scan for 90 degrees to detect any particular wall. Okay, so even if I sort of face anywhere, I need minimum 90 degrees to detect that there is the wall there. Right. So the 90 degrees is chosen because we want to detect one of the four walls. Okay, and since we know that we have 8 samples per degree, okay, because we have 2880 degrees per uh, per per scan. All right, so one scan is 360 degrees, so we have 8 samples per degree. Okay, so that's how we relate the samples to the angle. So once I get 720, that means that is the number of points or the number of samples I will get back. Okay, when I scan that wall. Okay, the number of samples I'll get back when I scan the wall. So after I scan the wall, I get 720 points. If the consensus is smaller than 720, then I can say that I get back more points than the consensus, so I can agree. But if the points I get back or the number of samples I get back is always smaller than the consensus, that means I do not have enough samples to come to an agreement that there is actually a wall there. Okay, like I said, consensus is like a minimum vote. Okay, so you need that minimum number of points so that you can agree that there is a wall or some obstacle there. If you never hit the consensus, then you will not be able to decide that there is actually something there.
So just to ask, right, so this means that we are calculating like the best case scenario where we just nice scan like an entire wall from one edge to the other, right? We will require 720, but in reality, we'll probably need more than 720 samples.
I mean, if you take any point, yeah, I mean, if you say that you are facing a random direction, right? Because even though you're facing a random direction, you are still trying to detect any of the four walls. So as long as you want to detect any of the four walls, when you scan, you need to have the points associated with this entire duration length of the wall, correct? So for that entire length of the wall, when you scan, okay, that is equivalent to a 90 degrees, right? It's equivalent to 90 degrees, which means that I need 720. You will of course get more points. You'll get the total of 2880 when you scan the whole thing, correct? But for me to detect that there is a wall, okay, or on any of the walls, I need minimum, I will get back 720 to represent that wall. Okay, so as long as I set my consensus to be smaller than 720, then I can say for sure that there is something there. Okay, if not, I cannot come to a decision, correct? I might just think that it's just some random points and it does not have anything that I can decide that there is there. Yeah, if you're able to meet the consensus value, then the ransack algorithm can confirm that there is a valid line there, okay, in its mapping. If we don't hit the consensus value, then it cannot conclude that there is a valid line there. It might just take it as some random points, okay, that does not uh, sort of agree to a obstacle or a wall being there. Okay, so let's okay, so that wraps up the questions. All right. So let me move over to the uh, requirements document. Okay, just to give me a minute. Okay, so this is the project specification. Okay, so I hope you've gone through this. All right. So what, like I said, there is no longer a color sensor, correct? So part of the project. So you can optionally choose to collect this. All right. And now this ultrasonic sensors and LEDs is LEDs again is up to you. Okay, you want to use it to add some nice color effects or whatever to your robot is fine. The ultrasonic sensors, you can collect up to 2 of them, okay? And if you choose to integrate, okay, then you can use them as also a way to maybe detect that you're close to a wall or something, okay, in your while you're maneuvering, okay? So that is again optional, right? It's not necessary, it's optional. Now, in terms of the grading, okay, we'll be using the same maze table, okay, that we use, okay, that is in the lab already. Okay, now when you do your testing, when you do your testing for the maze, okay, the setup, okay, what you should do is you should put up a more sort of a roomy uh, uh, setup. Okay, that means, okay, so let's say this is your maze. Okay, do not arrange your walls like how you use EPP1. Okay, where it's just enough for your robot to maneuver. No, okay, don't arrange them like that. Okay, keep a bigger space. Okay, so when you arrange your walls, try to keep a bigger space, okay, for your robot, and try to keep like a gap. Okay, so try to arrange something like this where you have a bigger gap, okay, between the two between the walls, okay, and you have an opening. So when you start your robot, okay, you must be able to maneuver, and using the LiDAR data must be able to detect that there is a gap over here. Okay, so you need to look out for the gaps. So you know that, okay, this is where I should go. Okay, so once I reach here, okay, then maybe you can have another setup, something like this. Okay, so once the robot comes here, then you will know that, okay, I have some space here, I have some space here, okay, and then I need to maneuver and explore. So the whole idea is while you're exploring, you should be able to map out and give accurate measurements of all these walls that you detect. Okay, so if you remember from the video, okay, there should be one person in your team that is doing the drawing. Okay, and through the drawing, you should also be able to accurately list out what are the dimensions. Okay, how many cm each of these walls are, these obstacles are. Okay, and then from there you maneuver until you finish up the whole maze, okay, the whole space. So that is the thing you should be focused on. Okay, so again, that is 90% of the mark. Okay, the mapping of the environment. Okay, so you need to submit. Okay, so again, you have to manually take note of the environment and you need to submit the map. Okay, now in terms of the evaluation criteria, if you see, there will be a 2-mark deduction for every 30 seconds over 5 minutes. So you have a total of 5 minutes, but maximum of 8 minutes. Okay, which means that you need to complete within, you should aim to complete the entire navigation within 5 minutes. Okay, so of course you still have up to 8 minutes, but you are going to lose marks. Okay, every time you go, once you pass the 5-minute mark. All right, you are allowed to do a retry. Retry means what? That means let's assume that Okay, your robot is here. Okay, and then for some reason it goes and then it gets stuck here, and then it just cannot move. Something just goes wrong. Then you can say, okay, you want to off and on and you want to restart. Okay, so you can restart. But when you restart, okay, your timer is still running. Okay, your timer is still running. So you should not try to do a restart. Okay, unless you're still early in the assessment. Okay, because your timer is still running. You don't have a restart of the whole timing. Okay, so your 5 minutes, 8 minutes is already starting the moment you do the first attempt. Okay, so as much as possible, try not to do a retry unless the very beginning itself something goes wrong. Okay, if you hit any wall or obstacle, there's also a deduction. All right, in terms of the marks, okay, so of course, how accurately you map out the environment, the distance, everything is the accuracy of the layout, everything is important, so that plays a part. Okay, now the additional functionality, okay, is 10%. Okay, so for this, again, within our studio group, okay, the first 3 teams will get this additional bonus marks. Okay, again, this will be, you won't know this until everybody has finished, correct? So we need to look at the total score, okay, for the teams. All right, and this we need to evaluate based on everything else that has happened. Okay, and then this additional 7%. Okay, so 1% is for TLS. All right, so if the TLS works for you, okay, everything is going well, you can use TLS. Okay, if for some reason the TLS part is not working out, or sometimes you always get error and it's very unstable or whatever, then you can choose to drop it and just use SSH and BNC. Okay, I think that 90% is still more important than this 1%. Okay, so you have to make a decision. If it is going well for you and you want to use it, go ahead. Okay, but if not, you can choose not to use it. Okay, then this 3% is the bare metal. Okay, so of course this is, if you do fully bare metal, that means everything is register level programming, then you get this 3%. Okay, if maybe partially you do, okay, maybe PWM and GPIO you do, but maybe serial and interrupts you use the sketch programming, whatever, then it's partial bare metal. Okay, so that is again something that you can think about. Okay, how much of bare metal code you want to include. All right, let me see. Then the other thing is all these deadline for submission. Okay, so you have your design report that is due by Friday 8 April, and the demo is on the 11th and 12th April. So it's on the Monday and Tuesday, okay, of the last week. Okay, so it's not the Wednesday and Thursday, it's on the Monday and Tuesday. Okay, so technically you have another 2 weeks left. Okay, that means week 11 and week 12 to finish up everything and wrap up the whole LX. Okay, because when you come in on week 13, there is no time already. Week 13 is the actual evaluation. Okay, actual evaluation day is like EPP1. That means when you come in, you are really required to I mean, basically you don't have time to extra, so you are required to submit your robots earlier. Okay, and then when you come in, you just do the evaluation. Okay, so it'll be something similar to EPP1 sort of assessment. Okay, of course you do not want to drain out your batteries and everything by trying and doing testing on that morning. Okay, so you need to make sure your batteries and everything are fully charged and everything is going well before you come in on that Tuesday morning. Okay, yeah, so anybody have any questions you want to ask about the evaluation for the project part? Okay, so like I said, the focus is again should be on this 90%. Okay, so make sure that this is the thing that you will spend more time on, making sure that you are very comfortable in your team, who is going to navigate, who is going to send the commands, okay, who is going to draw out the map. Okay, so that 90% is the focus. Okay, everything else, yes, if it works, it is going well, you add it in. Okay, then you get some additional marks. Okay, but if it doesn't, don't be too worried about it. Okay, make sure that the navigation part is the one that you are focused on. Okay, so of course one additional thing is this hump thing. All right, so this hump, I think most likely by next week should be there in the lab. All right, so we somewhere there might be a hump. Okay, the exact size and how it's going to be, you will see it, okay, once we put it up in the lab. Okay, and like I said, the way you know that there is a hump is because you're moving slowly. Okay, and then you come to a point where you try to move but you cannot move. Okay, why? Because you are hitting the hump. Okay, so whenever you can see that you're trying to move but the LiDAR map doesn't show any change, then there's a high chance you're sort of stuck at the hump. And that is where you need to backtrack a bit and then move forward with a slightly higher speed. Okay, so you can get over the hump. Okay, and then move on. Okay, so that is the only other thing that you need to also try out. Okay, once we put up the hump. Okay. Yeah. So does anybody have any questions? Okay, so I mean, we still have time, right? So over the next few studios, as much as possible, try to come in earlier. I think the lab is always open quite early. Uncle Jalil comes in, I think, by 7. Okay, usually he's in the lab by 7. So if you want to come in earlier, just go ahead and come in earlier. All right, and you can try to maximize the time, okay, to do all your testing and software, over the next 2 weeks. Okay, and of course, the rest of the team, if you're not doing the implementation part, then you can sort of split up the work and some of you can focus on the report. Okay, so that you don't get too stressed in the last week. Okay, so I think that's all I have for today. If you still have questions about this or the tutorial, you can stay back and ask. Okay, if not, thank you. I'll see you all next week.
Prof, can I ask what topics are tested for the quiz next week?
The topics, is it?
Yeah.
Yeah, the topics will be from ADC onwards.
Okay, thanks, Prof.
Yeah, but yeah, anyway, I think Colin will send out an announcement later. Okay, so okay, so for this, the character variable. Okay, so when you declare a character variable, it only occupies a single byte in memory. Okay, so when you only occupy a single byte in memory, when you're not able to test the Indianness, because to test the Indianness, okay, you need a multi-byte data. Okay, so you need 4 bytes or 8 bytes or even at least 2 bytes to know how the data is going to be arranged, so you can know whether the least significant byte goes to the lower address or goes to the higher address. If it's only a single byte, then it only occupies a single address, so you can't use that to gauge whether it is a big Indian or little Indian. Okay, so for this option 3, okay, so again, if you see down here, you can see that the data, the bits are sent out from the least significant bit, right? So the first is the bit 0, so this is bit 0. Okay, and then this is this is actually bit 1, correct, and then bit 2 and so on. Okay, it's just that it's always the least significant bit that is shifted out. Okay, and every time we shift that bit out, we shift the entire byte to the right. Okay, so it's always the least significant bit, and then the next bit and next bit and so on. Similarly, when I populate the byte receive, it is also starting with bit 0. Okay, and then bit 1, and then bit 2 and so on. So it's in the same order. When I transmit out bit 0, the byte receive, I also fill up bit 0. Then when I transmit out bit 1, I fill up bit 1 and so on. So the order is the same. And transmit and receive, I transmit and receive in the same order.
Prof, can you ask for question 1 of the past quiz questions? Why is it that we don't need to count like 0 volts as a possible voltage level?
You mean in this question?
Yeah, correct.
No, in this question, they've only allocated these 4 voltages, correct? So, I mean, it's up to the question, the way the question is phrased, correct? So in this question, they've only specifically chosen these 4 voltage levels as valid voltage levels in this sort of protocol. You know? So if I include 0, then I have 1 more voltage level, so I have a total of 10 symbols. You know?
Okay, thanks, Prof.
Yeah, the question never specify that 0 volts is used, correct? So we only use whatever they say. Okay, so the tutorial 4, okay, I will let Colin know, then maybe he will upload. Okay, so thank you. I'll see you all in the lab. Okay, bye.